Hello friends, I am Deepak Prajapati. I welcome you on my lecture series on complex analysis. In earlier lectures we have seen how to show that given complex function is analytic using Cosimon equations. Now in this topic we are going to discuss some particular complex functions. For example, we are going to discuss exponential function, trigonometric functions, logarithmic functions, inverse trigonometric functions, and complex hyperbolic functions. So we will see that these are just the generalization from real analysis to complex analysis. They are having some properties which are analogous to real functions, and there are some properties which make them different from real functions. So we will discuss all these functions one by one in upcoming lectures, and we will also discuss their analyticity, that at which points they are analytic in the complex plane. So in this lecture number 1 we are going to study complex exponential function. We will define complex exponential function, and we will discuss some properties of complex exponential function in this lecture. We are already familiar with real exponential function. If I consider any real number x, then e raised to x is the real exponential function, and it is defined for any real number. So we are going to study analogous part of this, that is complex exponential function. So we will consider z as any complex number. So here also complex exponential function is defined for any complex number z. So we start with the definition of complex exponential function. Let z is any complex number, say x plus iy. Then complex exponential function is denoted by e to the power z or exponential of z, and is defined as e to the power z equal to e raised to x into cos y plus I sin y. So we are using these three real functions, e raised to x, cos y and sin y. So using these three real functions we define complex exponential function, e to the power z equal to e raised to x into cos y plus I sin y. For example, if I have z equal to 2 plus 3i, then if I compare this 2 plus 3i with x plus iy, x is 2 and y is 3. So exponential of z equal to 2 plus 3i is, by this definition, e to the power x, that is 2, into cosine of 3 plus I into sine of 3. So this is the way how complex exponential function is defined. Now we study some properties of complex exponential function. This property is true for real exponential function. We are already familiar with this property in real analysis, and here we are going to prove it for complex exponential function. So if I have any two complex numbers z1 and z2, then exponential of z1 plus z2 is nothing but exponential of z1 into exponential of z2. So to prove this property, we start by taking any two complex numbers. So suppose we take z1 equal to x1 plus I y1 and z2 equal to x2 plus I y2. Then by the definition of addition, z1 plus z2 equal to real part of z1 plus real part of z2 plus I times imaginary part of z1 plus imaginary part of z2, that is y1 plus y2. We can prove in either way. Here I have started by our right hand side. I start from right hand side and I will show that this right hand side is nothing but e to the power z1 plus z2. So we start with right hand side, e to the power z1 into e to the power z2. Now z1 is x1 plus I y1. So by definition of complex exponential function, e raised to z1 equal to e raised to x1 into cos y1 plus I sin y1. Okay, we are using this definition. If z is x plus iy, then e raised to z is nothing but e to the power real part of z into cos y, y means imaginary part of z, plus I sin y. So here z1 is x1 plus I y1, so e raised to z1 equal to e raised to real part of z1, that is x1, into cosine of imaginary part of z1, that is y1 plus I sin y1. Similarly, z2 is x2 plus I y2. So e raised to z2 is e raised to x2 into cos y2 plus I sin y2. So we are simply using this definition of exponential function, and this we can simplify. This e raised to x1 and e raised to x2 are real functions, so we will combine them and we multiply these two brackets, cos y1 plus I sin y1, cos y2 plus I sin y2. So we take product of these two as a product of two complex numbers. Okay, we know how to multiply two complex numbers. Real part into real part minus imaginary part into imaginary part, plus I times real part of first into imaginary part of second, plus imaginary part of first into real part of second. And this is because x1 and x2 are real numbers, e raised to x1 and e raised to x2 are real exponential functions. So using the property of real exponential function, this we can rewrite as e to the power x1 plus x2. Now the product is cos y1 into cos y2 minus imaginary part sin y1 into imaginary part sin y2, plus I times cos y1, that is real part, into imaginary part, that is sin y2, plus imaginary part into real part, so sin y1 into cos y2. And if you concentrate here, this is a very famous identity of cosine function. This we can write as cosine of y1 plus y2, because y1 and y2 are real numbers and this property is true for real numbers. So cos y1 plus y2 is cos y1 cos y2 minus sin y1 sin y2. Similarly, this is also familiar identity. It is sin of y1 plus y2. We know that sin of y1 plus y2 is sin y1 cos y2 plus cos y1 into sin y2. So now if you concentrate on this, and if you concentrate here, z1 plus z2, z1 plus z2 is x1 plus x2 plus I times y1 plus y2. So by the definition of complex exponential function, e to the power z1 plus z2 must be equal to e to the power x1 plus x2 into cosine of y1 plus y2 plus I sin y1 plus y2. If I use this definition, if z is x plus iy, e raised to z is e raised to x into cos y plus I sin y. Now instead of z we have z1 plus z2, instead of x we have x1 plus x2, and instead of y we have y1 plus y2. So e to the power z1 plus z2 equal to e to the power x1 plus x2 into cosine of y1 plus y2 plus I sin y1 plus y2. So you can see this is nothing but e to the power z1 plus z2. So that is right hand side of our property. So we have shown that for any two complex numbers z1 and z2, e to the power z1 plus z2 is e to the power z1 into e raised to z2. Now using this property, suppose I take z1 equal to x here and z2 equal to iy, then I obtain e raised to x plus iy equal to e raised to z1 into e raised to z2, that is e raised to x into e raised to iy, and z is x plus iy. So we can write e to the power z in this short form also. Instead of writing e raised to z equal to e raised to x into cos y plus I sin y, we can simply write e raised to z equal to e raised to x into e raised to iy. Now if real part of z is 0, then z will be I into y. If in z equal to x plus iy, if x is 0 in z equal to x plus iy, z is pure imaginary I into y. So in that case, because x is 0, in the definition of e raised to z, we have to put x equal to 0. So e raised to 0 is 1 and we obtain cos y plus I sin y. Now z is I into y, so we put value of z here. So we obtain this very famous formula known as Euler's formula, e to the power iy equal to cos y plus I sin y, and it matches with this also. Okay, this is the reason why we are able to write e raised to z equal to e raised to x into e raised to iy, because e raised to iy is cos y plus I sin y, and this is true for any real number y. Next property is e raised to z1 minus z2 equal to e raised to z1 divided by e raised to z2 for any two complex numbers z1 and z2. Now this we can prove as we have shown in property 1 by taking z1 equal to x1 plus iy1, z2 equal to x2 plus iy2. But we will not go in that way. We will prove this property using property 1. So for that, to prove this formula, it is enough to show that product of these two, e raised to z1 minus z2 into e raised to z2. If I can show that product of e to the power z1 minus z2 with e to the power z2 is e raised to z1, then I have proved my property. So we start by taking product of e to the power z1 minus z2 with e to the power z2. Now if I consider z1 minus z2 as one complex number and z2 as another complex number, then using property 1 we can rewrite this as e to the power sum of these two exponents, z1 minus z2 plus z2. So here z2 will cancel out and we obtain e raised to z1. Okay, and if we take e raised to z2 on right hand side, we have proved this property, e raised to z1 minus z2 equal to e raised to z1 divided by e raised to z2. If you wish, you can prove this by taking z1 equal to x1 plus iy1 and z2 equal to x2 plus iy2. So depending upon the given question, depending on the instruction of given question, you should go appropriately. Next property, e raised to minus z is nothing but 1 upon e raised to z for any complex number z. So we will prove this property using this one. Okay, instead of 1 I can write e raised to 0. Okay, so I start from right hand side, 1 divided by e raised to z equal to e raised to 0 divided by e raised to z, and using this property, if we use in reverse way, e raised to z1 divided by e raised to z2 equal to e raised to z1 minus z2. So here e raised to 0 divided by e raised to z equal to e raised to 0 minus z, and that is nothing but e raised to minus z. Okay, so we have shown that e raised to minus z can be written as 1 upon e raised to z for any complex number z. Next property, if z is x plus iy, then absolute value of e raised to z is e raised to x, and argument of e raised to z is y plus or minus 2n pi. N can take the values 0, 1, 2 and so on. So to find out modulus of e raised to z, we have to first write down definition of e raised to z. We just discussed that if z is x plus iy, e raised to z is e raised to x into cos y plus I sin y. So if I take absolute value of e raised to z, then it is equal to absolute value of e raised to x into absolute value of cos y plus I sin y. Now if z is x plus iy, x is real number, y is also real number, and we know that e raised to x is always positive for any x in the set of real numbers. So therefore absolute value of e raised to x is e raised to x, and absolute value of cos y plus I sin y is square root of cos square y plus sin square y, and because cos square plus sin square is 1, this is going to be 1. So therefore if e raised to z is e raised to x into cos y plus I sin y, absolute value of e raised to z is e raised to x. Now if you recall the polar form of the complex number, we know that if z equal to r, if our complex number is in this form, z equal to r into cos theta plus I sin theta, then this r is nothing but absolute value of z, and this theta is nothing but argument of z, or we can write theta plus 2n pi to include all possible values of arguments. So if you compare this expression with this expression, z equal to r into cos theta plus I sin theta, so instead of z we have e raised to z, instead of r we have e raised to x, and instead of theta we have y. So if z is r into cos theta plus I sin theta, argument of z is nothing but theta plus 2n pi, where n is any integer. So again I repeat, if z is r into cos theta plus I sin theta, this r is nothing but modulus or absolute value of z, and theta is nothing but argument of z. So to include all possible values of argument, we write argument of z equal to theta plus 2n pi, where n is any integer. Now if you compare this z equal to r into cos theta plus I sin theta with this expression, then you can see e raised to z is already in polar form. So if you compare, then r will be equal to e raised to x, and e raised to r is nothing but modulus of z. Therefore modulus of e raised to z is modulus of e raised to x. That we have shown that absolute value of e raised to z is e raised to x, but that we can show from here also. If z is r into cos theta plus I sin theta, then this r is nothing but absolute value of z. So you can apply that logic here. Instead of z we have e raised to z, instead of r we have e raised to x, and instead of theta we have y. So if we have this type of polar form, then r is nothing but absolute value of z. So from this logic also, you can directly write that absolute value of e raised to z is nothing but e raised to x, and argument of e raised to z is nothing but this angle y. But to include all possible values, we will write plus 2n pi. So therefore argument of e raised to z is y plus or minus 2n pi. N can take the values 0, 1, 2 and so on. Okay, instead of writing in this way, we can write in this way also. Argument of e raised to z is y plus 2n pi. N is any integer. So both are correct. If I don't want to write n is any integer, I will write y plus or minus 2n pi, and the possible values of n are from 0, 1, 2 and so on. So this is nice property. If you know the definition of e raised to z, you can write down absolute value of e raised to z is e raised to x, and the argument of e raised to z is y plus or minus 2n pi. Next property is, we have to show that e raised to z is entire function, and as we know, entire function is that function which is analytic at every point in the complex plane. And to show that function is analytic, we have to first check its differentiability. And for differentiability, if you recall, we have used Cosimon equations. So first we check at which points Cosimon equations for given function e raised to z are satisfied. So we start by taking z equal to x plus iy. Then by definition of exponential function, e raised to z is e raised to x into cos y plus I sin y. And if I multiply this bracket with e raised to x, I obtain e raised to x into cos y plus I times e raised to x into sin y. And suppose it is equal to u plus iv. So if you compare, you have u equal to e raised to x into cos y and v equal to e raised to x into sin y. So we find out the first order partial derivatives. Del u by del x is cos y as it is, derivative of e raised to x is e raised to x. Similarly, del u by del y is e raised to x as it is, derivative of cos y is minus sin y. V is e raised to x into sin y. So del v by del x is sin y as it is, derivative of e raised to x is e raised to x, and del v by del y is e raised to x as it is, derivative of sin y is cos y. And if you recall, what are the Cosimon equations? Cosimon equations are del u by del x equal to del v by del y, and del u by del y is minus del v by del x. So if you concentrate on del u by del x and del v by del y, they are equal at any point x plus iy. Similarly, if you concentrate on uy and vx, then here we have e raised to x sin y, here we have e raised to x sin y. So we can write that uy equal to minus vx. If I put e raised to x sin y equal to vx here, I will see that second equation is also satisfied. That means both Cosimon equations are satisfied at every point z equal to x plus iy in the complex plane. So here I have written ux equal to vy and uy equal to minus vx at every point z equal to order pair xy in the complex plane. That is, Cosimon equations are satisfied at every point in the complex plane. Another condition we have to check is continuity of these four partial derivatives. So as we can see, these functions are nothing but exponential and trigonometric functions, sine and cosine, which are real functions. And we know that exponential and these two trigonometric functions are continuous everywhere. So we can directly write clearly ux, uy, vx, vy are continuous at every point in the complex plane. Hence, e raised to z is differentiable at every point in the complex plane. Therefore, if our function is differentiable at every point in the complex plane, it is analytic at every point in the complex plane. That is, e raised to z is analytic everywhere. Analytic everywhere means the function is analytic at each point of the complex plane, and therefore e raised to z is entire function. Entire function is the complex function which is analytic everywhere. So we can make some remark here. We have shown that e raised to z is differentiable at every point in the complex plane. So we will check whether derivative of e raised to z is again e raised to z or not. For real functions we have that idea that derivative of a real exponential function e raised to x is e raised to x. So by the definition or some result, if you recall, if f of z is u plus iv, we have shown this formula in any one lecture which I have uploaded on my channel. So f dash z is del u by del x plus I into del v by del x. So if function is differentiable at any point z, its value can be evaluated at that point using this formula. So here our function is e raised to z. So derivative is del u by del x plus I into del v by del x. Now del u by del x is nothing but e raised to x into cos y, and del v by del x is also e raised to x into sin y. So we substitute values of ux and vx here, and I take e to the power x outside, and we are left with cos y plus I sin y. But this is nothing but definition of e raised to z. So what we have shown is the derivative of e raised to z is e raised to z at any point z in the complex plane. Okay, so this is the reason why e raised to z is differentiable at every point in the complex plane. So I hope you like this lecture. In next lecture we are going to discuss one or two more properties of the exponential function, and we will do some problems based on this complex exponential function. So thank you very much.